For a slightly more practical example than number 2 from my previous video, let's look at number 12. We were told that a box with an open top is to be constructed from a square piece of cardboard 3 feet wide by cutting out a square from each of the 4 corners and bending up the sides. Find the largest volume that such a box can have. Now in the textbook, this is actually a multi-part problem. They walk you through a series of steps of exploring the problem and setting things up and working through it. If you would like to try that on your own, stop the video now, give that a shot, maybe explore the problem a little bit. Rather than following those steps, I'll just sort of dive in and run through the analysis to deduce the solution. We want to build a box with an open top out of a square piece of cardboard 3 feet wide. So we have a square piece of cardboard that is 3 by 3. And we're going to cut a square from each of the 4 corners and bend up the sides. So we will slice off little squares from the corners and bend up the sides. So these corners here will be removed, and we're going to use that to make, we're kind of bend those up to build a, to build a box, basically. So this right here forms the bottom of the box, and these 4 sides will be folded up, probably taped at the corners or something to hold them together. I'm sure you've seen this kind of little open top, like cardboard box or tray or whatever. These 4 corners will just be discarded. So we take this square piece of cardboard, cut out a square from each of the 4 corners, and bend up the sides to make a box with an open top. We are asked to find the largest volume that such a box can have. So the idea is that we have this 3 foot by 3 foot piece of cardboard, and we want to build a box that will hold as much as possible. So we want to maximize the volume V, which is length times width times height. Okay, so now that we understand the situation here, we need to represent this algebraically somehow. Let's describe the amount of the amount that we're cutting off. We're cutting out a square from each of the 4 corners. So let's call that amount x. So we have an x by x square that we are cutting out of each of these. So that means that the height of the box, if you look at what those x's amount to, the height of the box then will be x. How about these other dimensions? Well, we have this length of 3, and we're snipping off x from this end. We're also snipping off an x from that end. So the remaining length is 3 minus 2x, and that's the case on the other side as well. So we have 3 minus 2x, 3 minus 2x. That means that our volume is the height x times 3 minus 2x squared. We have a square of that is this long on each side, and then multiplied by the height of x. So this is our objective function. We are trying to maximize it. Let's, we'll need to look for critical points, which will involve a derivative. To make that easier, let's go ahead and square this thing out. 612 plus 4x squared. So then it looks like we have 9x minus 12x squared plus 4x cubed, if I have done this correctly, as our volume. Again, we want to maximize this. So let's find the derivative. V prime looks like 9 minus 24x plus 12x squared. And we want to use this derivative to find the critical points of V. This is defined everywhere, so now we set this equal to 0 and solve. let's rearrange this in descending order of powers and also divide through by 3. Right? We see there's a factor of 3 everywhere. So if we divide out 3 here, it looks like we have 4x squared minus 8x plus 3 equals 0. And can we factor this? I believe so. Do I want... not 4 there. Let's try 2x and 2x with a 1 and a 3. Will that give us what we need? We have minus 6x minus 2x gives minus 8x plus 3. That looks good. So this tells us that either x equals 1/2 or x equals 3/2. Well, which is it? Do we actually have 2 values of the maximum? Let's take a look back here and see what this is. X equals 1/2 or x equals 3/2. If x equals 1/2, then we get a box that is 1/2 high by twice that is 1, 3 minus 1 is 2, so that is 1/2 by 2 by 2. If x is 3/2, it's 3/2 high, twice that is 3, 3 minus 3 is 0. So actually, if x equals 3/2, we have a case where we have snipped away the box entirely, right? If we come in 3/2 this way and 3/2 that way, we've cut away the entire piece of cardboard. There's no cardboard left. Or if you imagine something just a hair less than 3/2, you have basically no base and 4 long, skinny bits that you're folding up together. You have practically 0 volume here. So this is kind of an extraneous solution. It's a critical point of the function, but it gives us a minimum instead of a maximum. It looks like this is what we're looking for. Let's make sure. I was using kind of the physics of the problem for this, but we could instead always use a first derivative test. Since we already have the first derivative computed and the zeros found there, we could say, okay, we have 1/2 and we have 3/2. Looking at this, if we take something smaller than that, like 0, you can see we have a negative times a negative is positive. If you take something in between like 1, you have positive times negative is negative. If you take something a lot greater than that, you get positive times positive is positive. So the function is increasing, then decreasing, and then increasing. And we see we have a maximum at 1/2 and a minimum at 3/2. And we wanted to maximize the volume, right? We were asked to find the largest volume that such a box can have. The maximum volume is, if x is 1/2, again, we got 2 for the other dimensions. So that looks like 2 cubic feet as our maximum volume. The 2 times 2 for 4 times 1/2 gives us 2. As far as the units, there are a couple ways we can see the units. One of them is just that the length measure is in feet. So just dimensional analysis, we have 1/2 foot times 2 feet times 2 feet, that's feet times feet times feet, that's feet cubed, or cubic feet. The other is just we're measuring our length in feet. We're trying to find volume. That makes cubic feet. It's probably good to think about both of those and make sure that they agree with each other. But there we go. We have just found that by cutting away 1/2 foot, 6-inch 1/2 foot squares off of each corner and folding up a box, we get the largest possible box, which is 2 cubic feet.